Let's use our first integrated circuit, the TL974 op-amp. Specifically, we're going to use it as a comparator. Okay, let's first start with integrated circuits. These are integrated circuits, or chips. Inside of these are devices that are made of many transistors. They're etched onto pieces of silicon. They're very tiny inside of this black epoxy housing, and the inputs, outputs, and power pins are wired to the legs that go into the breadboard. So inside of your kit, I've given you an extra breadboard with a whole bunch of chips. And the first one, the big one, is the TL974, which is a type of op-amp or operational amplifier. We'll be using those a lot in class and in lab. But for now, we're going to use it as a simpler version of an op-amp, a subset called the comparator. So a comparator does what the name says. It compares two voltages. So we draw it schematically as a triangle, and it has two inputs, the plus and minus input, or the non-inverting and the inverting input. And then it has a V out. So V out is going to be equal to the positive power supply pin, which we call VCC plus, or the negative output, VCC minus, depending on what happens to the inputs. So if V plus is bigger than V minus, V out will equal VCC plus. If V minus is bigger than V plus, then V out will equal VCC minus. Now, there are actually lots of different kinds of comparators, and some of them are subtly different than this. But if you're using a generic op-amp as a comparator, this is what should happen. So this is the schematic of the chip. There are 1, 2, 3, 4, 5 pins in this schematic, but our chip itself has a lot more. So what that means is we should look up the data sheet for this chip to figure out what pin does what. So I encourage you to go to digikey.com or Mauser or Newark or some similar, or Texas Instruments itself, and look for TL974. And you'll find a family of chips, the TL97Xs, and depending on how many comparators are on the chip, it might be a 1, a 2, or a 4 at the end of that number. And what you'll see is a diagram of the chip, and it will label every pin. Note that they leave out the caret for this quad chip. So this is a quad, meaning that it's got 4 op-amps on this one chip. But when you look at our physical chip, there's a divot at the top. There's also a circle at the bottom. The circle is the ejector pin where the machine that added the epoxy popped it out of the mold. We don't care about the circle. We care about this divot that's at the top. And the pin numbering starts at pin 1 in the top left and goes down to the bottom and then back around. This has 1, 2, 3, 4, 5, 6, 7 pins on either side, so it goes from 1 to 14. So this is pin 7 and this is pin 8. 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. And what it tells us is that this pin, pin 4, is the VCC plus, and this pin, which is 14, 13, 12, pin 11, is VCC minus. So what we'll be doing for this chip is we'll make VCC minus ground, and we'll make VCC plus 5 volts. So we need to build a circuit where we get 5 volts onto VCC plus and ground onto VCC minus. And we've got out, minus, and plus in the top left of the chip. So the top left of this chip is one of these op-amps, and then there are 3 more on the chip. So let's build a circuit that uses one of these comparators and see what it does. So let me draw the schematic, because before I want to build something so complicated, I probably want to draw what it looks like. So I'm going to have an op-amp. I'm going to attach the VCC plus to plus 5 volts and VCC minus to ground. That will power the chip. And I'm going to have an LED come from the output and go to ground. Doesn't really matter what color LED, but I always need to put a resistor in series with my LED to limit the amount of current. And I'll choose a 330 ohm resistor so that the indication LED is nice and bright, but not too bright. And then I'm going to attach the negative input to 2.5 volts. And then the positive, I'll just have be a wire. And then I'll just poke around my breadboard with that wire. How will I get 2.5 volts? Well, an easy way to get 2.5 volts is with a voltage divider. Two equal resistors. I'll use 1Ks. Two 1K resistors in series. The middle junction should output 2.5. So this is what we'll be building. I'm going to build it on my end scope because I already have power and ground in the rails. First thing I have to do is somehow get this chip out of my spare breadboard and into the Enscope's breadboard. And this is a little dangerous. These smaller chips is a little easy to do with your hands, but when it's a bigger chip, if I rip this out the wrong way, I might bend the pins and it'll be hard to get back out again. So I'm going to carefully wedge my pen under one side and knock it up a little, and then I'm going to go on the other side and get the other side so that it pops out. So that I'm lifting the chip out, not ripping it out, so that I don't bend the pins. And then I'm just going to choose some center area of my breadboard to put it back in. Sometimes you get a raw chip and the legs actually come from the factory, not so perpendicular, they come a little splayed out. So you would take the chip, hold it from both sides, and kind of roll it against a table so that you bend all of the pins at the same time. You don't want to bend them with your fingers. So once the pins seem like they line up the holes, I'll stick it in my breadboard. And it should lay nice and flush. And you want to look at the pins to make sure none of them bent under the chip and isn't actually touching inside the breadboard. Note that I'm also building against a hard surface of a table because if I build it up here in the air and plug it in, sometimes the metal inside the breadboard pushes back instead of accepting the wires. So I want to build something right against the table to make sure the pins are going into the holes. So what do I need? I need a 5 volts on pin 4. Pin 4 is over here to 5 volts. So my little red wire I've been using for a while, not long enough, so I need to cut a new wire. My ground wire, so on pin 11, I need ground. I can take ground from this side. And I'm using black for ground so that when I come back and I don't have to look at the datasheet again to figure out which pin was ground, I'll just try to remember, oh, that middle pin was the ground pin. And I take my bundle of wire and maybe I'll select a green wire. Green can also be used for power. And the way I cut this wire is I kind of eyeball it to say, oh, if one side's there and the other side needs to be here, I'll make it a little long, longer than that distance. And I'll remove the insulation from either side. And then I'll go from pin 4 to 5 volts. Okay, that's not ideal that this is a big loopy wire going across the chip, but let's not be too OCD about that. Okay, so now the chip is powered. Let's see if we can light up an LED. I'm going to use a green LED because it happens to be hanging out here. And pin 1 is my output. The LED is directional. The long side of the LED has to be more positive, so I'm going to take the long side of my LED and plug it into pin 1. And then into some other row of my breadboard. And then I need to find a 330 ohm resistor from my baggie. So you either have to learn the color codes or go with your multimeter and find what the values are. I know from the top of my head this is a brown, orange brown. I'll take a 330 ohm resistor. And I'm going to use the ground on this side of the breadboard because it's a little more convenient. And hey, look at that, my LED's on. I don't know, it's not super bright. And if I just kind of touch the pins, it seems to get brighter or dimmer. That's interesting. Because right now the op amp is trying to follow these rules to turn the LED either on or off. But I don't have anything plugged into these two inputs, so one might be bigger than the other at any given point. They're kind of just antennas hanging out in space. So this is probably blinking very, very fast as the chip thinks one or the other side's bigger than the other. Now I'm going to build my voltage divider to make 2.5 volts. So I'm going to do that up here. That's a 1K resistor to 5 and a 1K resistor to ground. It's probably a good idea that I check that with a multimeter first before or the end scope before saying that it has to be 2.5, but I'm pretty sure that's 2.5. Now I need to jump that over to the negative input, so pin 2. So I'm going to cut another wire. And I'll use a color I haven't used yet so that I remember this is kind of a unique size, so roughly that big. And the last thing I'll do is I'll take this long wire that represents my non-inverting input pin, and let's just plug it into 5 volts. So the decision the chip must be making right now is that 5 volts is bigger than 2.5, so I will turn on the LED. And if I move my wire to ground, well, now I'm seeing that that did not turn off my LED, so something must be wrong. So how do we debug it? I got out my multimeter. I'm going to go to the 20 volt setting because I know everything I'm doing is less than 20 volts, but probably more than 2. I'm going to slightly pull out this ground wire, but not all the way, so that I have something to touch. So I'm going to put my black probe on that ground wire, and then I'll poke around with my red probe to see what all the voltages are. So maybe the first thing I should check is, am I getting 5 volts on the pin of the chip? So I'll touch that pin and I see 5. I can also touch my ground pin, make sure I have 0 there. Okay, I'll touch the 5 volts on the voltage divider resistor, make sure I have 5. And I'll touch the output of the voltage divider to see, do I get 2.5? In this case, no, I'm getting 1.6. I'm going to pull out the wire that's connecting it to my chip. So now I get 2.5 like I expected, but plugging my wire that should go to the chip drops that down a lot. So something about my wire that's connecting my voltage divider to the input of this op amp is making it unhappy. So on further review of the datasheet, seems like this chip doesn't really like it when the negative supply voltage pin is at ground. Instead, really should go to -5. And I've added this purple wire so that the VCC minus pin is going to -5 instead of ground. We'll have to read in the datasheet to see exactly what's going on there a little bit more. But now we see, so our plus pin, when it's at ground, is less than 2.5. Our LED is off. And when the pin is at 5 volts, we're above 2.5 and it's on. So that makes this a very nice, like interesting chip. It's not really doing math for us yet, but it's making a decision, a yes/no decision. And that could very easily be used in a lot of things. We could, instead of turning on a light, we could turn on a motor, we could turn on a fan or a pump. So as long as we have a signal from somewhere, in this case, kind of a sensor, my sensor is just this random wire, senses something and can turn things on and off.